Okay, this video is a summary, hopefully, of all the metal aqua ion reactions that you need to know. You're familiar with this background of the slide, and what I'm going to do is I'm going to write on it and hopefully illustrate the main points that we need to remember, as well as the colours. The colours are just for you to remember. Okay, the first thing is when we are adding some sodium hydroxide, we're adding the hydroxide ion. And so we're starting off with the metal aqua ion, and we're making the hydroxide as we add the hydroxide ion, and we get the hydrolysis reaction. So that's a hydrolysis reaction, and when we do that for each one, so for iron 2, for copper 2, for iron 3, and for aluminium, all four of those hydrolysis reactions result in a hydroxide. So this one here is iron 2 hydroxide, this one here is copper 2 hydroxide, this one here is iron 3 hydroxide, and of course this one here is aluminium hydroxide. So that's what we get when we've added our hydroxide ions. Next thing to consider is, I'll just switch colour, let's go to blue, is the reversibility of this reaction. Okay, so when you do the opposite, i.e. you add hydrogen ions in the form of, say, dilute hydrochloric acid or sulfuric acid, you're going to redissolve the precipitates. These are all precipitates of various colours, and you're going to redissolve those precipitates. Now the hydroxides are then, if they're accepting those protons, they're acting as Bronsted-Lowry bases. So all these hydroxides are Bronsted-Lowry bases when they accept hydrogen ions and turn back into the aqueous ions. Okay, now can they do the opposite? Can they act as Bronsted-Lowry acids? Okay, by donating a proton? No, no, no. But this one, the aluminium hydroxide, as well as acting as a Bronsted-Lowry base, a Bl base, when it accepts a proton or several protons and turns back into the aluminium aqua complex, it can also donate another proton. So one of these protons here, one of these hydrogens, leaves behind its electron and donates the proton, or donates the proton to a nearby water molecule, forming aluminium hydroxide solution, which is redissolved and it becomes colourless again. So in doing so, when it is donating one of its protons from the water ligand, one of those two water ligands, so it's minus H plus, so this is now, that's donating a proton, and so that is acting as a Bronsted-Lowry acid. Okay, so this one, aluminium, can act both as a Bronsted-Lowry acid when it donates a proton from one of its water ligands, and it also reacts as a Bronsted-Lowry base when it accepts a proton from a hydroxide, when it accepts that proton to become to make the hydroxide ligand back into a water ligand. Okay, so that's why it's amphoteric, and it's only for aluminium because it's got the highest charge density on the positive ion, and for more detail on that I refer you back to the video. Okay, so that's some hydrolysis with sodium hydroxide and the amphoteric nature of aluminium aqua complex, or aluminium hydroxide as it happens. Let's move on. So I'm just going to get rid of that, and then we can talk about addition of ammonia, and you'll remember it's pretty much the same as addition of hydroxide ions. So you're going to get exactly the same compound. So you're getting iron 2 hydroxide, you get copper 2 hydroxide, you're getting iron 3 hydroxide, and you get aluminium hydroxide as well. So the thing to think about here is this one here. This is the unique one where you're also getting some ligand substitution. So at this reaction, when you add ammonia to the aqueous ion, that sets up an equilibrium, and it's an acid-base equilibrium, isn't it? Because you're taking these water ligands and turn them into hydroxide ligands by removing a proton. So that's an acid-base equilibrium, and that works, as you can see, for all four metals, all four metal aqua complexes. There is another possible equilibrium that could be set up, which is the ligand substitution equilibrium. That's the equilibrium between these two. However, it is only in the case of copper 2 that the ligand substitution happens. So the copper metal ion, obviously, for some reason, prefers the ammonia ligands to the water ligands, and so the equilibrium position is way over to the right in this reaction here, whereas in the other cases, iron 2, iron 3 and aluminium, the metal ion prefers the water ligands to the ammonia ligands, and so the equilibrium is way over to the left in this equilibrium situation, in the ligand substitution equilibrium. And so that's the only case where you get a ligand substitution, and when you do so, your precipitate redissolves and becomes a solution again and changes colour from blue to deep blue. So that's the one thing you need to, main thing you need to know about ammonia and the addition of excess ammonia. What we can do now is talk about carbonate. So again, I'll get rid of that and talk about carbonates. And here we notice that we have a big difference between the carbonates of your metal 2+ ions, right, and your carbonates of your metal 3+ ions. Because with your metal 2+ ions, that's this one, and iron 2 and copper 2, you get a simple metal carbonate, right, precipitate. So there's iron 2 carbonate and there's copper 2 carbonate by a simple reaction where the carbonate combines with the metal 2+ ion and forms yourself a insoluble compound which precipitates out, okay, of those particular colours. Now, what you will remember is that these complexes are only weakly acidic. They're only weakly acidic, okay, and so they're not acidic enough to decompose the carbonate ions that you add. So the pH of these might be a pH of probably 4 to 5, around about 5. Whereas the pH of our 3+ ions here, the pH of these is going to be 1 to 3, about 2 probably. So much more acidic, and for why refer back to the video. But because you have much more acidic solutions, then we are going to decompose our carbonate ion, and that's a two-step reaction. You get, first of all, you get hydrogen carbonate ion, and then another proton joins that and forms a water molecule and carbon dioxide. So carbon dioxide is evolved, and instead of a carbonate you get the hydroxide. So you get iron 3 hydroxide and carbon dioxide, and the iron 3 hydroxide here looks just the same as your iron 3 hydroxide here, and your aluminium hydroxide here looks just the same as your other aluminium hydroxide here, and in fact here and here as well. So you get your hydroxides and your carbon dioxide gas, right, where with the two acidic solutions, and you just get simple carbonates with your two less acidic carbonates. Okay, I think that was point number 3 I wanted to make. Last point, let's just get rid of all that. Last point is about iron. Iron 2 hydroxides. Okay, so when we make these, hopefully what we'll see, but if you don't, you need to know anyway, is that you'll have these green solutions, these green hydroxide solutions, with green precipitate floating around. And if we leave it open to the air, at the top of the test tube, i.e. the bit of the solution that's closest to the air, you're going to see a brown layer at the top. Alright, of those, I'm going to say the top bit, the bit that's touching the air in contact with the oxygen, turns brown. So the green precipitate is no longer green at the top, it's brown. And it's this brown here, because what's happened is that this iron 2 has oxidized into iron 3, which is this one, which is brown. And that's what happens when it's in contact with the air. And that's the last, that wasn't in the video, so that's why I wanted to make that point there. So that's the last little summary point, the 4 summary points there. Hope that's helped you appreciate this table here.